All right, this is problem number 58 from chapter 13. And I promised to work a problem somewhat like this, and then I realized that the problem I was going to work is from your homework. So anyway, I'll read it to you quickly. Two springs are attached to a piece of cloth A of negligible mass, as shown. The initial tension in each spring is 500 newtons, and the spring constant of each spring is K equals 2 kilonewtons per meter. A 20 kilogram ball is released from a height h above A. The ball hits the cloth, causing it to move through a maximum distance d equals 0.9 meters. Determine the height h. All right. Well, let's sketch the systems as we wrap our heads around what's going on here. So there's two springs, piece of cloth. And a ball that's dropped from some unknown height, h. Now, the deflection that occurs is a maximum deflection d of 0.9 meters. So basically the ball ends up on the pouch here at a distance like that. Okay? Now, we're also told that just from the figure, and this is symmetrical, I won't draw both sides. We're told that the center of the pouch to one of the supports is 1.2 meters. Now, the spring constant is 2 kilonewtons or 2,000 newtons per meter. And the initial force in each spring, let's just write F naught, is 500 newtons. Okay. Now this is very similar to the last problem, but where students frequently run off the rails is they begin to think, well, let's see, some force equals mass times acceleration, so I have to somehow quantify how the spring force varies as it moves from here down to here. As the ball impacts and then moves from here to here, I need some way of writing down the force in the spring. And you could actually figure it out. You could draw a free body diagram of basically just the pouch, and you could come up with the equivalent force acting upward on the ball, or what the ball would have to act down on the springs to get it to move. But that's a waste of time. This is an energy chapter, right? We use energy. The nice thing about energy is not just that you get to neglect usually the directions of things. You also get to neglect any intermediate things. So if you find yourself trying to figure out what goes on in the path from one state to another, you're wasting time. Okay? So let's see if we can figure this out without considering what happens in between. In fact, let's go from state 1, where the ball's up here, down to state 2, where the ball's down at the bottom of the pouch and the springs are fully stretched, or however far they're going to be stretched. Okay? Now, what do we know about state 2? If we were to write down an equation, an energy equation that says T1 plus sum U1 to 2 equals T2, what do we know about both T1 and T2? The ball is released from rest.
It equals 0.
That's right. The initial velocity is 0. So the initial kinetic energy is 0. If this is the maximum distance that the ball reaches, then the kinetic energy at state 2 is also 0. Okay? Now we're not going to have an equation that just says 0 equals 0 and there's nothing else in it. Whatever the energy is in here must balance out. Okay? So what different forms of energy change in this system? Well, gravity, right? So gravity does work through a distance. And then there's also the springs, right? So as we go from state 1 to state 2, what happens? Well, just this. Negative W, delta Y. Gravity does work on the ball. Just like it was before, right? What else happens? Well, the springs go from one state to the next. So plus 1/2 K delta X 1 squared less delta X 2 squared. That sums 0. Now we haven't figured out what delta x1 and delta x2 are yet. We'll do that along the way. But the idea here is that all of the energy that was in the pellet, or whatever this thing is, stone, whatever it is, all the energy in that mass is now moved over into the springs. That's all that's happened here. So all we have to do is figure out the height h, because see, we know how much energy the springs begin with and end with. We don't have a number for it yet, but we know we can figure it out, right? Because we know the initial force in the springs, we know the final stretch of the springs, we know the spring constant. We should be able to get a number for this piece. And then we know part of how far the thing fell, but we don't know all of it. So basically delta y is the unknown, and delta y is just going to be the sum of h and d. Now we have to be careful though, because it's going to be the negative sum of h and d. Does that make sense? Because delta y has to be a negative thing. So let's write that down. Delta y equals the negative of h plus d. And h is really what we're looking for. Now we're going to have to figure out delta x1 and delta x2 at some point. So let's bite the bullet and do it. Okay? If the force in the spring, let me show you a quick way to deal with springs. This will make it easy. The force in the spring versus delta x. Well, that's all the room I've got on the video just about, so try not to go off the video screen. Now, we don't know the free length of the spring. We'd probably like to find that out, because we'd like to get delta x2. But we do know a data point. We know that at a length, in fact, let me do it this way. Instead of delta x, let me plot this versus length. At a length of 1.2 meters, we know that the force in the spring is 500 newtons. Put that here. So the units are newtons and meters. Okay? Now, the other thing we know is that the spring constant K is 2,000 newtons per meter. What does that give us? Well, that essentially gives us the slope of this line. So if we were to increase by 1 meter, if we were to move over to, say, 2.2 meters, well, then the force in the spring would have to go up to 1,500 newtons. Or, I'm sorry, 2,500 newtons. Does that make sense? For a change of 1 meter, we need a change of 2,000 meters. Okay, it's easy enough. So, it'd be nice to know the free length of this spring. How can I do that? I'll just bring this back down and solve for it, right? Now, I made this go through the origin. That's not correct, obviously. My scale is bad here. It should look more like this. I'm going to go through the x-axis at some non-zero value of length. Well, where would that be? Well, it's pretty simple. If we need to move down by 500 newtons, then we need to move down by 1/4 of a meter. Does that make sense? Because if I move down a whole meter, I'll move down 2,000 newtons. That's too much. I don't want to move down 1,000, so I don't want to move a half meter. I want to move 1/4 of a meter down, right? Now you can go through a lot of work to figure out the slope, intercept, whatever. If you remember how to do that, you can do it, right? I'm not in that mode right now, so I'm not going to go that way. I'm just going to realize the numbers work out nicely. I need to come down here 1/4 of a meter. So what is this length here? What is the free length? 1/4 from 1.2, right? So 0.95. Does that make sense? So the free length of the spring, I see people shaking their head no.
I don't get that.
All right. Let's back up. We're at this data point, right? Let's erase this for just a minute. If I were to take the spring and move it by 1 meter, how much should the force in the spring decrease? 2,000 newtons. That's what this says. You move by 1 meter, the force changes by 2,000 newtons, right? So if I decreased by 1 meter and I would decrease, right, because I'd be releasing the spring, of course I'd end up compressing it, but what would happen is this would have to move down to negative 1,500 newtons. Make sense? So if I were at, put it over here, my scale's really bad here. Let me cheat a little bit, increase that slope. So if I moved it all the way down to 0.2 meters, where that was the length of the spring, I would be all the way down at negative 1500. Let's see, let me put this, so the other data point would be here at negative 1500. Because I've come down 1 whole meter, right? If I come, you just told me if I come up a meter, then it has to increase by 2,000. So if I go down a meter, it has to decrease by 2,000. So I would go from 500 down to 1,500. I don't want to go that much distance, right? Let's try going 1,000 instead. And in other words, let's only move a half meter, okay? So if I subtract a half from 1.2, what do I get? 0.7, right? So that would be 0.7. That would be the length. So if I take this down to 0.7 meters, then the force in the spring would be negative 500 newtons. That's still too far, right? So I'm going to move half that distance. In other words, I'm going to move down a quarter of a meter, and that will decrease the force by 500 newtons, which is exactly what I want. So if you take a quarter from 1.2, you get 0.95. Does it make sense now? A little more? Okay. Any questions? I don't mind going over any of this again. Everybody okay? All right. So basically, the point here is that the free length, L sub F, is 0.95 meters. Okay, and that's what I needed. So now I can calculate delta x1 and delta x2 very easily. Of course, really, if you, well, I won't go into that. Okay, so 0.95 meters is the free length. At the initial state here, we've got 500 newtons in the spring. So the deflection is 1.2 less 0.95. So the deflection at 1 must be 0.25. Right? Because the distance between 1.2 and 0.95 is 0.25 meters. So there's our initial deflection. Okay, how about the final deflection? Well, the final deflection, we can actually calculate, right? If this distance is 0.9 meters, let me extract the triangle so you can see it. Okay, so 0.9 meters, 1.2 meters. How would you figure out the length of this side? Square root of the sum of the squares, right? So if you take 1.2 squared plus 0.9 squared, square root, what do you get? It's probably some decent round number.
1.5.
How much?
1.5.
1.5, thanks. So 1.5 meters is the length. So we don't go all the way up to 2.2. Instead, we've gone up to 1.5. And so whatever that force is, we'd like to know. Now, we don't really need that force. We could figure it out. But what we really need is the deflection. So if this is 1.5, then the difference between 1.5 and 0.95 would be delta x2. So this would be 1.5 less 0.95. Obviously, that's what, 0.55? Okay, so 0.55 meters. And so now we have numbers for all those things. Okay. Does that make sense so far? Okay.
Can you just delete the graph?
You want me to get rid of this?
Yeah,
Is that okay?
yeah.
Everybody okay with that? Just get rid of that graph. It was too confusing. Just